Greetings and good evening, minions. I, as always, am Nathan. I am a PhD student, and I am a few months away from graduating, I certainly hope. And yeah, I'm just here to talk about some chemistry, because I'm an enormous nerd, and apparently I don't do enough of that for my day job, essentially. And so I come on here and I talk about more chemistry because I think it's really fun, and I think this is something that a lot of people find less fun than I do, and can struggle through it somewhat. And so I'm here to offer my services. Cheesiest of cakes. Happy Tuesday. It is so lovely to see you again. I hope you are doing well, my friend. Yeah, haven't seen you in a little bit. So I did a short stream on Friday, because today is Tuesday, and I missed last Tuesday. But yeah, I am back, and I'm excited to go through some stuff. Yeah. So as always, I've got a problem set that I will work through, and just talk about some questions, and just go through some of the concepts a bit. But let's see, I've been good. Missed the last stream, crunching on exams. Very, very fair. It is that lovely time, isn't it? I've been doing all right. This last week and a bit has been kind of a lot, which is why I missed last Tuesday. But this is that happens, and things are fine. Yeah. Looking forward to getting back into it a bit. Yeah. What was I saying? Sometimes I forget. Yeah, so as always, I've got stuff to kind of fill time. But if you have any questions about anything in particular, I'm more than happy to focus on whatever that is. And cheeses with cakes. I'm glad you're here, cause I was thinking today of talking a bit more about orbitals, just what they are, how they work, and how a little bit of how we use them. Because I think it's last time we were on the stream together. Oh, no worries. Sweat. You get to it when you get to it. No sweat at all. I am forever behind on my reading as well. So don't worry about that. Yeah, orbitals. Because we had been talking a bit about just kind of how reactions work. Last time that you and I were chatting on stream a bit, and got into talking a little bit about orbitals, which I think is something that was kind of poorly explored before you get to maybe about second year of undergraduate chemistry or some such. And so I just want to talk a bit more about fundamentally what those are, because it's going to be really different, I think, from how things are introduced in high school chemistry, but it's not that hard to get the basic concept, which is of course all I'm going to really be getting into, because it's not as if I prep for this or anything. So yeah, it'll be a pretty basic overview. But I hope it'll make some sense. And of course, once we get going on that, feel free to stop me at any time. And yeah, we'll get into it a bit. But, alrighty, got your notebook handy. Very, very good. Okay. So let's go over here. Very good. So on Friday I went over SN1 and SN2 reactions in some more detail. We went through some mechanisms. This I you know how sometimes you look at something that you drew a few days ago, and you're like, good lord, that's a mess, is what that is. But there is some level of order to this chaos, and of course the full explanation of this as I went through it is on my YouTube channel. And so like, it looks kind of chaotic when it's just up here all at once, but there is a reason that I wrote all these things. I'm not going to go over all of it, of course, but I'll go over just briefly what we did. So there's this first reaction here where we were taking this little heterocycle, which is just a cyclic compound that one of the members in the ring is not carbon, and how we use HBr, which is a very strong acid. It's not a terrifying acid, but it's something that needs to be handled carefully and given a lot of respect. Mostly because of the propensity of hydrobromic acid to form bromine, Br2, elemental bromine, which is something that is very, very hazardous. And I saw the aftermath of a bottle of bromine having exploded just a little bit, and it was not my research lab, but one of the adjacent labs. It's just this is the one of the hazards of working in a chemistry lab. Is it was stored in a cabinet for who knows how many years, not even improperly stored or anything, but it exploded and it made a gigantic mess, and a really, really hazardous mess. But anyways, that is neither here nor there. Yeah, so essentially, with that reaction, we started here, and there's two directions you can go, because there's in this mechanism to get from reactants to products, there's an SN1 reaction and an SN2 reaction. And the SN1 reaction goes like this, where you have this molecule. So you protonate the oxygen, which is the first step in whichever way you go, because this makes it a really reactive oxygen. And so it's looking to take electrons from wherever it can. So going the SN1 route, it takes the electrons from here to form a carbocation on this carbon that is a tertiary carbon, and it does that so that the carbocation that it forms is, you know, the least bad carbocation that you can make, because carbocations are electron deficient. They only have 6 electrons around a carbon, so it's an incomplete octet on that carbon, which is not at all favorable to form. It's pretty difficult to do that. You have to have some fairly harsh conditions, such as, you know, being in a strong acid like hydrobromic acid, and even then, in order to form a carbocation at all, it needs to have some level of stabilization to it. And so that's what we were talking about here, where when you form this carbocation, the carbon with the positive charge, in essence, it becomes far more electronegative. So it wants electrons, and it will pull on them from anywhere, because now it's an unbalanced charge. It has more positive charge than negative charge, because it's got the same number of protons, but it's had electrons taken away from its valence shell. And so it pulls very hard on the electrons in the bonds around it, which partially offsets that positive charge. So this becomes a positive charge with a partial negative. So it becomes basically less bad of a positive charge, and it makes the other carbons around it slightly more positive. So each of them gets a partial positive charge, and that's what stabilizes this carbocation, because as with 98% of chemistry, and you're going to hear me say this a thousand bajillion times, 98% of chemistry is just reducing electron-electron repulsion, spreading out electron density as much as possible. So that's what happens there. And then once you've formed that carbocation, it is very, very quickly going to react with anything that can act as a nucleophile, which is an archaic way of saying a source of electrons. And that is the Br minus that we form in the first step here. And so that comes and makes half of the molecule, and then we rinse and repeat. We protonate that oxygen again, and it forms a very good leaving group, so that that another bromine, because we were told in the question, whoop, that's other stuff. So we were told in the question that we've got excess HBr, which means we can use it as many times as we want. So that can come in and act as a nucleophile here. But this has to proceed by SN2 because we don't have that intermediate step where we form a carbocation and then react it. But yeah, and so that just comes in, kicks off neutral water as a very good leaving group, and that's it. That's the target molecule here. Jesus. All right, I apologize. I will be back in just a minute. Someone's at the door. I'll be back in a moment. Hello, I'm back. All right, yeah. So it's you probably heard my doorbell, which is my dog. Yeah, our actual doorbell doesn't work super good, but hello. But thankfully, Callisto is vocal. Whenever anybody is at the door, so it's hard to miss. Alrighty, so getting back to the review, yeah. So this, right? It's so good, and oh man, so like part of the reason, so when we were deciding on her name, we were down to. Because we really like the Greek mythological names. Because our old pupper that he died a few years ago. It was named Achilles, and oh, he was such a good boy. What a sweetie. But then we got Callisto, and of course Persephone and Daphne are the cats, and those are both also Greek mythological names. Anyways, so when we were deciding on Callisto's name. We were down to either Callisto or Calypso. Both very good names. Oh, yes, he was the best boy, thank you. But yeah, so Callisto or Calypso. But then my partner looked up a picture of Callisto, which is one of the moons of Jupiter. And it's all like speckly and really pretty. And so is Callisto, because she's part blue healer, and so she's got some of the spots and the dappling, and so she kind of looks a little bit like the Moon Callisto, and that just decided it for us. But yeah. Yeah, I've had lots of Greek mythological names in our pets. So we had a bearded dragon a few years ago before we moved to our new place. We had to get rid of him, unfortunately, but his name was Icarus. Oh, that's right. And originally the bearded dragon's name was Icarus. And then one day Icarus laid eggs, and we're like, oh, you're not a boy. So Icarus became Kyra. But anyways, yeah, I very, very good floofs, and pets, reptiles are also good. Yes. Yeah. So this reaction, you can. There's two very valid ways to go about it. The SN1 reaction followed by the SN2, or you can do the SN2 reaction first, which is just exactly the same thing, essentially in reverse, and the SN2 followed by the SN1, which I think is actually more likely because SN2 reactions are intrinsically faster than SN1. But anyways, I think that is all the time I'm going to spend on that for now, because we went over it quite thoroughly in the video that's up on YouTube, the most recent one. So, now, want to get into talking a bit about orbitals, because orbitals are they're completely essential in how we think about just molecules in general, in how we rationalize like reaction mechanisms. Hey, that's all right. That's fine. Yeah. So orbitals are essentially like the way that we describe how chemistry happens. And so yeah, we talked a bit about some different models of the atom, and so we were talking a bit about. I'm just going to turn this music down a little, at least for me. Let me know if the music is louder than I am, because I can't super tell. Anyways, so yeah, we went over like the some of the different historical models, like the kind of plum pudding model, which was like the I think it was from Thomson, which was basically saying like atoms are this solid mass with like kind of positive and negative charges throughout. And that's just they're just kind of this lump of stuff that has charge distributed throughout it, and that wasn't a super good way to think about molecules, because then I believe it was Rutherford came along, and what Rutherford did is he set up this I think it was this little like source of electrons, and so he set up this gold foil, and so gold foil is unique because gold is so extremely malleable that you can like hammer it down until it is like a few atom layers thick. So it gets you these extremely thin sheets of gold, and so he was trying to elucidate some properties of what atoms are. And so he shot I believe it was electrons. Someone correct me if I'm wrong. But he would shoot these little electrons at the gold foil, and so when he did that, a surprising result of this was that many of these electrons, they may have been neutrons actually. Now that I'm thinking about it, so I'm just gonna put that in there because those might have been neutrons. So the surprising result was that a lot of these particles, neutrons or electrons, that were shot at the gold foil went straight through and just impacted this detector that Rutherford had set up. So this was kind of surprising, and this kind of put the final nail in the coffin of the plum pudding model, because now we knew that this network of gold atoms couldn't possibly be this kind of solid mass. It couldn't be this opaque, like, full wall of atoms. And so this is when we got to to a model of the atom that was more like this, where you had all the positive density in the middle, and then electrons, negative charges were further away. Because not only did there's a second result of this, because he also set up a detector along here. Because the amount of particles getting through the gold foil was less than the number of ones that were shot at the gold foil. So what he was finding was that some of these particles did not go through, but they got deflected by the gold foil. And so what this led Rutherford to believe, to conclude rather, was that there's a small region of the atom where these particles, I think they must have been neutrons actually, but anyways, neither here nor there. So there's a small region of the gold atom where it will cause deflection. So if it like hits the nucleus, then it'll deflect in essentially a random direction. But like having this second detector kind of perpendicular to the foil was what caught those deflections. But noticing that like most of them went straight through, you conclude that this central mass must be very small compared to the total size of the atom. And so that's how we got into that kind of planetary model of the atom. And this was not the final iteration of this model, because then there was Niels Bohr, who articulated the different energy levels that electrons must occupy around an atom. But essentially, this is how we found out that atoms are separated into a nucleus, and then which the electrons orbit around. And now I'm remembering how we got onto this in the first place, because one of my little chemistry pet peeves is when people say things like, "Oh, atoms are 99% empty space," which is utterly false. It's not true at all. Because once we got into the paradigm of quantum chemistry, now we have these. Now we've got these descriptions of what electrons are doing around the atom, and this is how we got into the subject that electrons exist in these orbitals, and we must get away from thinking that electrons are strictly just these small particles that you'll have that orbit the nucleus, because it's like let's say if they were particles, so we've got a nucleus here and we've got an electron in orbit around it. So if this were a particle, and then it would have it's got mass, it's got it must have speed and momentum because it is going around a nucleus, and so it must excuse me if it was a particle and obeying like strictly like Newtonian physics, then whenever it turns to continue orbiting the nucleus, it like that requires an input of energy to maintain its speed, right? Because one moment. Callisto likes to be loud sometimes. Alright. So, where was I? Right. So yeah, if we were to assess electrons by strictly Newtonian physics and treat it as a particle that is orbiting a center, then as it goes around, the change in the direction of its speed, which is to say like the because the change in direction is a change in velocity, and so it is then subject to this equation, which dictates that acceleration, which is can just be like the electron turning to continue orbiting the nucleus, requires force, and so by strictly Newtonian physics, electrons would very, very quickly lose energy as they orbit, and they would spiral into the nucleus. But clearly that doesn't happen because we exist. So it cannot be that electrons are continually collapsing into the nuclei. So they cannot operate by Newtonian physics. They must operate under quantum physics, which introduces wave-particle duality. And so when we say that electrons orbit a nucleus, that's not really a correct thing, as kind of a misnomer these days, because they kind of don't orbit crap. They exist in these orbitals, and the electrons exist as a standing wave function. So it doesn't collapse because of wave function duality. Essentially, yes. They don't collapse because they're not in motion around a nucleus. They exist kind of at all of these points around the nucleus. Okay, so that is supposed to represent a wave function. Kind of looks more like a blob, but that's okay. So yeah, these electrons, like because they are such incredibly tiny particles, they have a discernible wavelength, and so like they exist as these wave functions that are just they just are around the nucleus. They're not at any particular location at any given time because of the Heisenberg uncertainty principle, which says like we cannot know precisely the position or the momentum of a small particle, like light scattering. I guess if you could observe light stays in the direction it's scattered. I think like light scattering. Yeah, very very closely related to that, I think. Um, if you observe light, it stays in the direction it's scattered. Um, so when light is scattered, uh, so let's say this is some particle in the atmosphere, and when a photon of light um, comes and interacts with this particle, um, then it can, depending on the properties of the particle it encounters. Hello, Percy. Um, the light will scatter in the like it will radiate essentially off of that particle, and it radiates in all directions. Let's say it's so. Yeah, like this is why the sky is blue, is because light from the sun is interacting with particles in the atmosphere. Usually it's like very tiny particles of dust, dirt, debris, and stuff like that. And when it hits these particles, it radiates light in all directions. And just because of the kind of distribution of size of particle sizes in the atmosphere, the portion of light that is most efficiently scattered is blue light. And so that's why it happens. So yeah, the light hits a particle and then radiates, which is why the sky gets bright before you ever see the sun, because the light is hitting the atmosphere and then radiating to the ground beneath that atmosphere. So we don't have to be in the direct line of sight of the sun in order to see, which of course is not the case on the moon, where there is no atmosphere. On the moon, there is none of that, and it is the moon is only illuminated on the parts of the moon that are directly in in the path of the sunlight, with the small exception of the light it gets from Earth, because sometimes you'll see like a little crescent moon, but you can kind of see the outline of the moon, and like very dimly you can see the rest of the moon. But that's because light hits Earth and reflects off of the moon, the face of the moon that's facing us, and then comes back to us. So the kind of dark part of the moon that you can still sort of kind of see is called Earthshine, because that is, you're seeing light that is has reflected off of the Earth and then hit the moon and then come back to the Earth. So that's what's going on there with light scattering, and yeah, like electrons will do the same thing. They have different properties, because of course, like electrons are not photons. Because electrons, first of all, have mass, and because of that, they have generally a much different wavelength than photons of light, because photons are like the kind of particle that's associated with light, because light, of course, also has this wave-particle duality. So yeah, like this is the answer to why electrons don't collapse into the nucleus, is because they exist as these essentially like standing waves around the nucleus that exist in orbitals, and and so what? Actually, I just want to take a very small tangent. That I heard a pretty good analogy the other day of how you can think about this, about the kind of wave particle duality and like, so in. Hey, leave that alone. Hey, quit it. No, you can go look out a different window. You don't have to look out this one. It's too bright. Can I get a boop? Thank you. Okay. Don't do it. Hey. Yeah, that's better. Okay. Sorry, like that's just my cats will always get priority in this stream. No, I'm not sorry for that. Who am I kidding? Anyways, right. So, good way to think about wave particle duality for electrons. Of course, absolutely. Is if you think of like a drop of water that has like a little tiny grain of dirt in it. So like electrons exist in these orbitals around a nucleus that have like a defined size and shape, which is like quite large compared to the size of what an electron is as a particle. And so if you think of like a little like couple little drops of water just in a little bead, but then there's this grain of dirt in it, and that's kind of like this wave particle duality. The space that it. Hey, get your face out of there. Ooh, quit it. I know it's very exciting. Just leave. Stop wrecking my blinds. I'll just get back on track. Right. So, so like the whatever. So the little puddle of water is like the kind of size and shape of an orbital, and the electron is like it. And this is kind of where quantum chemistry gets a little confusing, and it's okay if it's confusing. Like both of these things are the electron. The electron is the wave function that takes up all this space, but the electron also is that little particle that's floating around in this little droplet of water. So that's one way that you can think about it. And this is kind of the struggle of quantum physics and wave particle duality. And I assure you, it does not make a ton of sense to me either on a surface level, because like none of this is like things that we can intuit. But components of a whole. Yeah, I'd say that's a reasonable statement for sure. Because like it's essentially it's both of these things at the same time. Like both of these are properties of the electron, and yeah, like quantum physics, quantum chemistry, is a strange, unintuitive thing that like it doesn't make sense to anybody right off the bat, because we don't have any sort of common sense about this, because we didn't like we've evolved to observe and react to a macro world around us. Like I like this glass is to me like a perfectly solid object, and the first time that this was told to me, it made no sense that I'm holding it up right now because of electrostatic interactions between my fingers and the glass. It's all electromagnetism that prevents my finger from going through the glass, and lets me grip it and hold it in the air, defying gravity in order to do it. But yeah, it's okay that it doesn't make sense to me, because the nature is under no obligation to make sense to us. It is what it is, and it's our job to set aside our biases and really investigate what it actually is. Still trying to think of a way to imagine this, but my mind keeps getting stuck on the blue and black, white and gold dress. Sure, yeah, and that's a meta. Kinda, yeah. Like it is sort of similar to these things too. I think those go on a little bit of a so the different colored dress, or the Yanni Laurel thing. Um, this is kind of pointing out just like how our brains just like do weird things without us knowing about it, um, and how like um, how our internal biases affect our experience of the world. Like how our brains are wired to expect input um, affects how we actually experience these sounds and sights and all of this stuff. Because brains do so much more than just like receiving input and just, well, like that being our experience. No, it interprets, our brain interprets those inputs as well, and then runs them through filters of our biases and our so like all of these unconscious mechanisms that have that we've evolved to, well, to survive, really. Um, just like the like pattern recognitions. The classic example is a tiger in the bushes. If you're out in the jungle and you see some bushes rustling, uh, you could assume you could assume that it's the wind or that it's a tiger. And like you might look at the bush and see, like you might think you see the pattern of a tiger, and then you book it and you run away, and like that pattern, the pattern of a tiger may or may not have actually been there, but your brain said it was there, based on minimal information, and like because you ran away from a potential threat, you live to see another day. Because if it actually if it wasn't a tiger, then yeah, you've expended a little bit of energy, but other than that, like you got some exercise and you'll be fine. But if it was a tiger, then you survived, and you did not become lunch, assuming it didn't chase you because it's lazy. Is it like oobleck, the cornstarch water thing being most solid and liquid? So there's definitely some parallels that we could draw there, that it has these kind of dueling properties. But oobleck and cornstarch water things, which are those are called what is it? I think it's like Newtonian fluids. Is it something like that? But those are not a direct parallel to what electrons are and wave particle duality. It's not the same thing there. Because like, yes, they do have properties of both solids and liquids under different conditions, but these are emergent properties from the basic chemical interactions of the suspension of cornstarch solid in a liquid, and so like there's a kind of a categorical difference there. But it's also not a bad thing to think of, to be like, hey, this has properties of two different things that we've identified. Yeah, no worries. Like it's all very much a process to like actually have any understanding of what goes on, and like rest assured, like I am somewhat qualified to talk about like wave particle duality, because I get like kind of the I understand some of the practical effects of wave particle duality. Um, but in terms of like the fundamentals of it, or like being able to picture what this is like in my head, not even close. I have no intuition as to what these would look like. I have like very little like understanding of like how these mathematically exist and all that. So like this is difficult stuff. And there's a certain amount that like I am going to have to ask you to trust me on, as I have trusted my professors on. Because at the end of the day, I don't fully understand quite a bit of this stuff, but I understand it well enough to relate it down to things like orbitals, so that we can talk about them and get some understanding of their properties and start to build up at least the intuition of the kind of macro scale chemistry that these affect. Okay, so that brings me to orbitals. So, in talking about orbitals, these are like mathematically what orbitals are. These are solutions to what's called the Schrodinger equation, and I do not understand any of the math that is going on. I've been showed it, and once I was done with that class, it immediately left my brain, and like maybe it'll come back someday, but today ain't it. Because like also I was being taught by a really bad teacher, like a lovely person and a brilliant scientist and a terrible teacher, which is unfortunate. But so the Schrodinger equation. So the solutions of the Schrodinger equation are what define the shape and the size of orbitals around atoms, and so so there's a few different kinds of orbitals, and they're called S and P and D, and then like F orbitals. Those are all that you are ever going to have to deal with. Like maybe far in the future, we'll discover extraordinarily large atoms that make use of things like g orbitals, which theoretically exist, but are never used in any kind of practical chemistry, because we don't have atoms that utilize any orbitals above f orbitals. Even f orbitals are very rare, because only the largest atoms that we know, like the lanthanides and actinides, which like uranium and plutonium and neptunium and all these ones with weird names that I haven't memorized because why would I? Those are the only ones that utilize f orbitals. So I'm not actually going to worry about those too much right now. I'm just going to describe the first three, and these are ones that we do deal with in chemistry quite often. And so these are just like different categories of orbitals that have different shapes to them, and a few different properties that we'll talk about. So s orbitals are spherical. I honestly do not know if the S is for spherical. It would be fitting if they were, because that's their shape. But I don't know. It's probably got some other like obscure Latin root that someone decided was a good idea, and then it just kind of stuck. But I don't know the story behind why they're lettered the way they are. let's not worry about it. So, s orbitals are spherical. They exist in a perfect sphere around a nucleus, and so that's their properties. They're pretty boring. P orbitals are shaped like kind of an elongated figure eight, or or number eight, or whatever. And when we get to P, whoa, oh great, nice, well done, Nathan. When we get to P orbitals, we have to start defining the phases of the electrons. And I'll get into what those phases are in a little bit. Wait, is it an entirely perfect sphere, or just from our view, like viewing the Earth from beyond space? So it is a theoretically perfect sphere. And I say theoretically because the Earth also is theoretically spherical, but because the Earth is rotating, it is slightly flattened. So it's slightly elongated at the equator versus the poles. So the Earth is actually an oblate spheroid. But that's not a good parallel to what this is. So an s orbital is spherical, unless it is in the presence of other orbitals, and then they will influence each other and change the shape a bit. Because remember when I was talking about orbitals before, they can have interactions where if they're in the same phase, they'll act like two bubbles that are floating in the air, and they meet and then just go into one big orbital that's kind of like now it's kind of an ellipsoid, but they're certainly not spherical anymore. Or they can, if you have s orbitals of opposite phase interacting with each other, then they're like balloons. And if you squish them together a bit, they'll deform from that kind of spherical shape, and they'll push up against each other. They'll squish and they'll squoosh. So they don't end up being spherical in practice. But if they were totally isolated from any other effects, they would be a perfect sphere. Yeah. So, is it the only thing that's perfectly spherical, or could the nucleus be a perfect sphere? That's a good question. And so again, I wouldn't even say that this is a perfect sphere, because in practice, all of these are influenced to whatever minute degree. All of these orbitals are influenced by the presence of other orbitals, other electrons, and so it's So it's and even then, like, it's really hard to define exactly what the shape is, because this is also just a region which contains the wave function of an electron, right? Because the orbital is the actual orbital is a mathematical solution. So it defines an area where it is how shall I say this? It defines an area which contains the electron density. So here I think I know how I'll talk about this. So how do we do this again? Would it be more spherical? Is it if it's a smaller thing, like an orbital versus nucleus? I'm not entirely sure how to answer that. So like, right, I was going to say, because you asked about whether a nucleus was a sphere, and I do not think that a nucleus would be considered spherical unless it is a hydrogen nucleus, which is just a proton, and that probably could be said to be theoretically perfectly spherical as well. But again, that is also influenced by the presence of every other particle around it. But in every other nucleus, you have protons and neutrons, and those are bound together by the nuclear forces. And I don't see any reason why those should be spherical themselves. Those should have more discrete particles, kind of just globbed together. Yeah. No, fair enough. Like these are good questions. Want to in talking about this. Not density. Probability. So this is where the atomic properties get kind of weird, and like it's okay if you don't fully understand, because this stuff is weird. It's not intuitive at all, so electrons exist in these orbitals, and so the space that the wave function of an electron occupies, it's often described as a probability density, which is to say, like if we've got nucleus here, and I'm just going to put a little circle around you. So that's the nucleus, and if you got a spherical orbital here, it's like the chance a certain area is occupied. Yes, exactly that. So like this sphere is just like peppered with all these like this effectively infinite number of little points. These little what shall I? Sorry, I'm just debating. So like, it's say like the electron could be here or here or here or here or here or here, or any of an effectively infinite gradient of positions around the nucleus. And so that's what's being described by this probability density. So the R is the distance from the nucleus. Nucleus. Okay. Does it ever occupy the same place more than once? So, I mean, it could. If I'm understanding your question correctly, it could occupy like this point multiple times. Not of course at the same time, but it could theoretically occupy the same space more than once. And so I guess another way to kind of put this is like maybe not so much individual points as does this work maybe? No, I want this one. No, I want this one, obviously. No, that's not what I was hoping this had kind of like a spray function like paint. Yeah, so like at different times it could occupy the same space, but like it's not going to occupy multiple spaces at the same time, if that makes sense. Because like both of those, because it has to obey the Heisenberg uncertainty principle. So like we can never know exactly where it occupies, because if we knew the exact position of the electron, then its momentum would be effectively infinitely variable. uh, and which is like not a physical possibility, um, which which is why like the like you can't ever know the precise momentum. Here's like an application of the Heisenberg uncertainty principle, because it's like the I can't remember the mathematical formula for it, so I'm not going to worry about that. But it's saying like the Heisenberg uncertainty principle essentially says that the more precisely you know the position of a particle, any particle, um, any like very tiny particle that operates under quantum physics. Um, it's like the more precisely you know the position, the more uncertainty you get in its momentum. So like the direction and the velocity of the particle, and the other way around as well. The more precisely you know the the velocity, like the momentum of a particle, the more uncertain its position becomes. So basically, if you were to measure with infinite precision the momentum of a particle, like let's just say I've got an electron here in my fingers, and I know exactly what direction it's going and exactly the speed of it. So I know its momentum perfectly. Because of how quantum physics works, because of the Heisenberg uncertainty principle, that electron now could be literally anywhere in the universe, because you know its momentum perfectly. So its position is infinitely uncertain. So it could be literally anywhere in the universe, and you would not know. And this is why like the Heisenberg uncertainty kind of prohibits the precise knowing of momentum or position, because you get to basically an absurdity if like something that is not logically consistent, if you know one of these things precisely. Is there a reason why that occurs, or does it just happen? There is absolutely a reason, and effectively it's math. And some people who are so much smarter than me have figured out the math behind this. But like this does this governs how things like the double slit experiment work, and how like whenever we and the observer effect as well, because anytime we measure a particle, be that a photon of light or an electron, like we measure it with instruments that effectively detect either an electromagnetic. Well, actually, I think they're all electromagnetic. Okay, just one moment. So, one moment. Double slit experiment, because velocity is controlled in a precise manner. So the it does work on that same principle, but it's more because like in a double slit experiment, the position of these things is more controlled, and so like we can measure when you fire these through slits, as the position of them gets confined to the slits, the momentum becomes more and more uncertain, because when it passes through the slit, then it radiates out, right? Because you have doot, and you get like electrons coming in, and effectively like these are waves as well, but once they get to range of position being set, yes, exactly. So when the electron, which has this wave has these properties of a wave and the properties of a particle, so as it approaches the slit, its its position here becomes very confined. I'm going to make this a little bigger, and maybe try and make it less bad. Okay. Okay, so let's just say that the electron is approaching this the double slit. So once it gets to the slit, its position is confined, and so when that's the case, its momentum becomes highly uncertain, and like it can take on any of a number of vectors from that slit. So it can go this way, it can go that way, it can go that way, and what you see in an experiment for when you have multiple slits. Let's just put that in a different color. Actually, let's do. So when it gets to either slit, its position gets confined, but its momentum gets less defined, and so it can go in all of these directions. And so what you see, what you end up seeing on the detector is a diffraction pattern. So you get these discrete lines on the detector because they interact as waves interact, and so they have all of this momentum in all of these different directions. Could any of the electrons end up going back from the slit it came from, or is it limited to 180 degrees? That is a great question. I believe that it's I believe that the momentum would be conserved in that an electron that hits a lot. Well, no, that's not entirely true either. So yeah, no, I think you're entirely on the right track here, because remember, like those arrows that I've drawn here are not representative of what an electron is, because remember, like electrons have this wave particle duality, and so they travel as waves, and so when they hit the slits, they will, like, there's a certain amount that will go through and will create diffraction patterns on a detector over here, but certainly there's a number of them that will bounce off of the areas around the slit, and those will go backwards as well. Like when it hits the slit, it's not just going to just change direction backwards, I don't think. Although I would definitely have to ask someone who is much better at this than I am. But certainly, like, because of the properties of the electrons, there's a possibility that it will not go through the slits, but will bounce off of the barriers around the slits and radiate this way. So that's certainly possible as well. So it's like, yeah, so it's you have to have many electrons being fired at this double slit in order to get any of these results, the diffraction pattern. But like if you set up detectors here, you'd certainly get some that are deflected that way as well. And as always, please don't be sorry for detours. Like I'm just a happy little clam here, just here to talk about science. This is fun for me. Okay. All right. So right. So let's talk about this probability density graph. So basically, this is what this is saying is that there's a space, like, so this is, if this is 0, so this is on the x-axis, this is this point here is the nucleus, And so there's very, very little. I should really draw it from like there. So there's no electron density at origin here. So there's no electron density at the nucleus, but there is electron density all around the nucleus up to like a certain point where this peaks, and then it goes back down. This is actually not super well drawn. I'm going to make this better. Okay, so 0 electron density at the nucleus, very quickly goes up, and then just kind of slowly diminishes, and this area of the electron density only goes to 0, like only goes to exactly 0 at infinity. So like it's the electron has a non-zero chance of being like out here instead of somewhere in here. So like this area around the nucleus where the electron exists, this is what we define as the orbital, and where you have, you know, a essentially an extremely high probability of finding the electron here, a very low chance of finding it here outside the orbital, and infinitesimal chance of finding it way out in nowhere. So closer it is to a specific distance, the more likely it is to occupy. So the higher the point on the graph, So the like there is this kind of point of maximal probability of finding it, and that is kind of like within the confines of this orbital. So the R is just some arbitrary distance from the nucleus. But yeah, essentially this is describing like there's going to be basically nothing at the nucleus, but like out here in a little distance away from the nucleus, that's where the orbitals occur. Like the ground say having more electrons. Yeah. And so like if you okay, so let's say that pink here is an excited state. So if you take this, call the blue the ground state. If you take an excited state, I think what you'd more likely see is something like a little more like this. And so in an excited state, you're more likely to find the electron being further away from the nucleus than it is in a ground state. So yeah, like that's totally applicable here. And remember this. It's important to note that the probability of finding an electron, it's not saying that, there's more electrons here than there are like down here, because this is saying like an electron. And so okay, I'll get to your questions in just a minute. I'm just going to finish this up before it slips away, because it's likely to. So like this is not describing the number of electrons you're likely to find. This is saying like if an electron is occupying this orbital, then it is most likely to occur at this distance from the nucleus. So this isn't describing multiple electrons. This is like this is basically this is the graph of where you'll find one electron orbiting or like in an orbital around a nucleus. Excuse me. So would it mean that the electrons are more scattered in an excited state? If that's what you're meaning, yes. An excited state, like the electron has, it takes up more space, and you have a higher probability of finding it, further away. And so in that sense, yes, it is more scattered. Is uranium or unstable elements all excited? No. So even unstable elements like uranium that decay over time, um, it would not be correct to call those or to say that those are in an excited state. That's not accurate. They are the nuclei of those elements are fundamentally unstable, and at some time, they will decay. The nucleus will split apart. Um, but that's not the same thing as saying like this is an excited state of this molecule, because the ground state or excited state is talking about electrons that are around a nucleus, and just like what energy levels those electrons occupy. Okay. Right. Hey, we'll take 70%. That's awesome. um, okay, so orbitals can be an S orbital, and those are spherical. They can be a p orbital, and those are kind of this elongated figure eight. And d orbitals are essentially like well, most of the d orbitals, I should say, are essentially like two crisscrossed p orbitals. And again, like these shapes are just dictated by the mathematical solutions of Schrodinger's equation. Don't ask me why they occur like this. I have no idea. But like, I think if anything, this should be it should be comforting that like you don't have to like fully understand the quantum mechanics of these things in order to be a good chemist, which I will humbly submit that I am. So yeah, you can get to a very advanced level in chemistry without knowing all this like quantum physical hand waving. Well, thank you so much. That's so kind. I appreciate it. Okay, so these are the basic shapes of the orbitals, and so every orbital can hold two electrons, up to two electrons, and they cannot have more than that. Like it could have 0, 1, or 2 electrons though. And again, just very briefly, blah, English is hard. Chemical reactions happen when there's essentially a rearrangement of electrons, and this can happen by a full orbital with 2 electrons overlapping with an empty orbital that has 0, or it can happen with a singly occupied orbital which has 1 electron overlapping with another singly occupied orbital. Those are basically the two paradigms of how reactions happen. Is you have filled or partially filled orbitals interacting with partially filled or empty orbitals. And so when we're talking about, so I wonder, I want to. What do I want to do? I want to go grab a periodic table because I had one in one of my other whiteboards. It'll just take but a moment for me to get it. Do the thing, please. Thank you. Last time. Okay, where's my periodic table? I'm certain I had one. Where did it go? Oh yeah. Ruh-rohs. Okay. We're just gonna we're just gonna find one. Okay. You look like a nice periodic table. Yeah, it's fine. It's fine. Oh, what if I can just copy and paste? That would be terribly convenient. Yes, very good. Okay. Okay, so let's put you here. All right. Yeah, actually, so this is kind of useful. In this periodic table, they're divided into S block, P block, D block, and F block, which you may notice is the designation of the orbital types. This is terribly useful, and I will explain why that's the case. But one thing important to note is that helium over here is part of the S block, and I'm not going to heavily get into why that is, but this is a pretty good start, I think. Maybe just a little more over here. Very good. Okay, so there's a few identifiers for the elements, and those describe what sort of electron configurations they have. So basically, it says like how many electrons do they have, and what orbitals. Oh God. Okay, English is getting hard. So this is my cue that my brain is getting a little fried, and soon I'm going to have to wrap up. But I'll go through a bit more of this at least, so we get a little bit of a foundation of what this is. So, the descriptors just tell you how many electrons an element has and what orbitals those occupy. Wait, for P and D orbitals, is the nucleus in one of the big spaces of the figure eights, or is it in the middle of the eight or crisscross eights? It would essentially be in the very middle there, because so this graph of probability density is different for s orbitals than it is for p orbitals or for d orbitals, and so those they take different shapes. Like a p orbital would look like something like that. I think for next time, I'm going to actually look up some of these probability density graphs, because they're a really good way to understand like what's going on in the orbital. I don't think we'll worry about it right now, because we're kind of not there yet, but we definitely will get there. So that's something I'm going to make a quick note to myself to look up, because if I don't make a note, it will leave my brain and it will never come back. Yeah. Okay. Okay. So I'll look that up for next time, for Friday, and hopefully I will sound like I know what I'm talking about at that point. But yeah, so essentially the answer to that is that the nucleus would be in the very center of this, because it would be like nucleus here, and then one lobe of the p orbital would be like that, and the other would be like that. And p orbitals. Nope, not there yet. We'll get there. Just a moment. There we go. Okay. So when we're talking about this, so this number is important because this states the energy level. And so like a hydrogen will have 1s1. So this is how we denote the electron configuration for a hydrogen atom. So hydrogen has one proton, and as a result, as long as we're talking about neutral hydrogen, which we are, it will also have one electron. And so the electron will occupy the lowest energy orbital possible, at which, again, that is the ground state. So this all ties into what we were talking about with ground states and excited states as well, because a ground state electron occupies the lowest available energy level, which is, say, like the lowest energy orbital that is not full. And an excited state will have an electron occupying an orbital that is not the lowest energy orbital available. So, but in principle, electrons in a ground state, and unless I say otherwise, I'm always going to be talking about a ground state. So when we have just one electron, the lowest orbital, the lowest energy orbital is a 1s orbital. So that's saying that it's in the first energy level, and I'll explain what the other energy levels are in a minute, because it's not necessarily intuitive. So first energy level in an s orbital, and there's one of them. If we have... So the second element, helium, has 2 protons. It's got an atomic number of 2. So it's got 2 protons in the nucleus, and as a result, it will have 2 electrons. And because every orbital has room for 2 electrons, the electron configuration for helium is going to be 1s2. So again, that means it's in the first energy level, it's in an s orbital, and there's 2 electrons in that orbital. Because something that I sort of kind of totally forgot to mention is that the sp and d orbitals, that is also the order of how of the energy of these things. So the energy, I'm just going to draw another stupid little graph. So energy getting bigger, going this way. So we start with a 1s orbital, then a 1p orbital, a 1d orbital. It's important to note, does not exist. There is no such thing as a 1d orbital. And as I'm saying this, I'm realizing that I'm a silly boy, because there's also no such thing as a 1p orbital. So that was, yeah. This is gonna happen. I'm gonna make mistakes. It's fine. Doesn't always feel good, but that's okay. So the energy level number 1 only contains an s orbital. So the 1 and 2 here are referring to, this has 1 electron. So let's call this, oh, come on, A, B, x. A equals energy level, or this can also be called an electron shell. And I am writing behind my head, so let's go here so you can see that. So yeah, A is talking about the energy level. B is talking about orbital type. And that's the S, the P, the D, etc. And then the X is how many electrons are in that particular orbital. Okay, so that's the notation that we'll use for describing these energy levels. There is only a 1s orbital in the energy level number 1, and the next energy, the next lowest energy is a 2s orbital, because we start here at hydrogen, and we go way over here to fill up the helium orbital with electrons. And then we have to start back at the next row of the periodic table. And that's where we go to the second electron energy level. And we start with lithium. And so that has a... let's go over to... So lithium has an electron configuration of 1s2, 2s1. So this is saying that lithium has 2 electrons in its 1s energy level, and it has 1 electron in its second energy level. And so beryllium would be 1s2, 2s2, because we always fill up each orbital level before we move on to the next. So it goes to 2s, and then the next energy level is 2p. Because once we fill up the 2s energy level with lithium and beryllium, then we go over, we stay in the second row, but we go over to boron. And boron here has the electron configuration of 1s2, 2s2, 2p1, because this is in the p block, and so the energy of the orbitals goes up in that order. So 1s to 2s to 2p to 3. Whoa, that is a terrible 3. To 3s to 3p, and that's what takes care of like this row here. This third row is the 3s orbitals over here, and the 3p orbitals here. If we go over to, let's say, oxygen, so the electron configuration of oxygen. So oxygen has 8 protons, and as a result, it has 8 electrons as well. So it has 1s2. Excuse me. So, 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then it has 4 electrons in the 2p. Right, because it's got 8 electrons, so 2, 4, 8. So So this is the electron configuration here. Now, you may be wondering why I have put 4 electrons in the p orbital, because an orbital can only handle 2 electrons. That is because p orbitals have there's multiple orientations of p orbitals. There's and and always specify your electron phases, because it's important. Okay, so p orbitals come in 3 flavors. There's pz, py, and px. So because here it's, so this is how can I'm trying to think of the best way to describe a p orbital, because of course it's hard to signify this on a 2-dimensional space, but these are 3-dimensional orbitals, right? Because this is a sphere. Even though I have gone through no effort to draw it as a sphere, it's just a circle here. But these are also like 3-dimensional, so they've got like 3-dimensional lobes on them. I'm not sure how best to describe them. Let's yeah. So here's a pretty good way, actually. Okay, so you can kind of see that behind my face there a little bit. Let's move this down a little bit. So these are the 3 the 3 orientations of p orbitals that all coexist. So there's along the x-axis here. So this blue one is the px orbital. The red one is along the y-axis, and so that is the py orbital. And the black one is along the z-axis, and so that is the pz orbital. So we have to make these distinctions. There we go. That's the right one. Between the orientations of the p orbitals, because each of those can carry 2 electrons in them. And so just like in this picture, the p orbitals are all 90 degrees from one another, right? They're all along the different axes of a Cartesian coordinate system. So these are all the term that's usually used in chemistry and math is they are all mutually orthogonal to each other. So they are all at right angles to one another, so that there is no overlap between p orbitals. So px does not overlap with py at all. It cannot. Pz does not interact with py. It does not overlap whatsoever because it can't. And so that's why there can be up to 6 electrons in the in the collective p orbitals. But I want to show you a different way that we'll sometimes use to signify orbitals. So for helium, remember helium has just 2 electrons, and they're both in the 1s orbital. And so we would just designate this box is the 1s orbital, and it contains 2 electrons in it. And so that's another way of representing the electron configuration of helium. And if we go to oxygen, we would go this. So this is 1s. This is 2s. And this is 2px, 2py, and 2pz. I'm actually going to... So there's different stuff about that I want to talk about later. But for now, I'm going to use neon instead of oxygen. So neon would be very similar to oxygen. It would have 1s2, 2s2, 2p6. So that's the full electron configuration for neon. It has 10 electrons and this noble gas configuration. And note that in the second energy level, there are 8 electrons. And this is the stable octet. This is the thing that is required to follow the octet rule when you get into such things. Is like is just like the s and p orbitals together being full is the so-called noble gas configuration. Neon is a noble gas, so that tracks. Okay, so if we were doing the electron configuration like this for neon, we would have the 1s orbital is full, the 2s orbital is full, and then the 2px, 2py, and 2pz are also full. So that's just another way that we use to represent the electron configurations. It's probably one that I will make frequent use of from here on out, because it's a pretty succinct way to identify which electrons are where. Because if we were to go down one to let's say F, which is fluorine, so it's got 9 electrons instead of 10. So it would just look like this, with the 1s, 2s orbitals are full, and 2 of the p orbitals are full, and 1 of them is half filled. And that's kind of the I guess ground state electron configuration for fluorine. And just note that I could just as easily have taken one of the electrons out of the 2py orbital and left the 2pz orbital full, because all of these p orbitals have exactly the same energy. So there's no preference in terms of energy as to which of these get filled by the electron, by the order that you fill these up in by the electrons. So I think the last thing that I want to get into about orbitals today is things called quantum numbers. And this, so I was thinking about quantum numbers the other day, as one does, really. 'Cause why wouldn't you? What I was thinking about is how quantum numbers were explained to me very poorly when I was going through my intro chem and just learning about this for the first time. These were explained very poorly, and I don't think they need to be, because these are not too bad. I'm gonna hydrate a little bit, and then we'll talk about it. Um, every electron in and out, like no matter what element we're talking about. Like we could be talking about uh, rhenium or platinum or germanium or hydrogen. Uh, any element on the periodic table can the electron configuration can be described by quantum numbers, and so this is there's four numbers. There's n, there's l, there's ml, and there's ms. Now, it's not super important what these what these terms actually mean, because what these are is these numbers n, l, ml, and ms. All of these are variables in the Schrodinger equations. And depending what each of these numbers is, the Schrodinger equation gets solved to be a different shape or size or orientation of an orbital. Like these are the variables that we use to build up these mathematical solutions of all the different orbitals, the s orbitals and the p orbitals and the d orbitals and the f orbitals and all the other orbitals that we don't ever use because they just, well, they're for elements that we haven't even discovered yet. Don't worry about that. So these are all variables in the Schrodinger equation, and they describe, like, so each electron in any electron configuration has a specific set of quantum numbers, and a unique set of quantum numbers. So essentially, what these are, the quantum numbers, these are like coordinates on a map to find a specific electron. Like these are an electron's address, whether it's in the first energy level or the third, or an s orbital or a p orbital. It is like these quantum numbers are the specific address for an electron. So n can be any integer that has an r greater than 0. So so n can be any integer greater than 0, and so it starts at 1, and the n is the energy level. As this goes, I actually would like to move this over here. Yes, good. Okay, so yeah, so the quantum number n starts at 1. It can be 2, it can be 3, so on and so forth, and it's just describing the energy level. So 1s, 2s, 3s, 4s, 5s. These are all described by the energy level, by n. So L is what tells you, is this S, is this P, is this D, is this F, or is this, some other orbital? But yeah, for all intents and purposes, we're going to stick to these. And so this is, so L describes the orbital type, and it can be I'm running out of room to write stuff. So it can be described by any integer equal to n minus 1. How am I going to say? Okay, let's put some stuff up here because this is getting too cluttered. So n is an integer greater than 0. L. I'm just going to be anal about this and put colons instead of equals. So L is any integer equal to how do I describe this? So it can be greater than or equal to 0 up to n minus 1. So I was saying for if the energy level is 1, which is the lowest one that's possible, then L can be up to n minus 1, which is 1 minus 1, which is 0. So for something in the first energy level, 0, 1. Sorry, I'm getting distracted, but it's for a good reason. So in the first energy level, L can only equal 0, which means that it can only correspond to an s orbital, which is why when we're filling up, or when we're even just talking about orbitals, we fill up the 1s orbital, and then we have to go to the next energy level, because the only orbital that energy level 1 can contain is an s orbital. Okay, so I want to say ml. Okay. Okay, so oh, actually, I know. I want to. Sorry, I'm just needing to get a little more organized than I actually am. Okay, so L, in an energy level 1, L can only be 0, which means it's an s orbital. In energy level 2, now L can be either 0 or 1, right? Because it's an integer. It can be 0, and it can be up to n minus 1. So if n is 2, now L can be 0 or 1, which means it is either s or p orbitals, which is why we go from 1s to 2s, and then we stay in the second energy level, but we now have access to p orbitals. So ml is ml is referring to orientation, which means it can be px, py, or pz. So I didn't include anything for s because s orbitals are spherical. They have no orientation, or rather they have exactly one orientation. Because ml can equal integer from negative L to positive L. So this is saying that when L equals 1, which is to say when we are referring to a p orbital, now ml can be either If this is 1, then it can be -1, it can be 0, or it can be +1. So once we have a non-zero L, once we have a p orbital, now we have access to different orientations, and in the first, in the second energy level, we have access to 3 orientations of that. So that corresponds to px, py, and pz. I'm going to fill this out a little more. So if we have 0, 1, or 2, which is s, p, or d orbitals, right? Because once we get into the third energy level, then we have to start taking d orbitals into account. That's usually so d orbitals are filled up when we get to the transition metals. They're a little bit oddly placed because they're level with the fourth energy level, with energy level 4. I'm not going to explain why that is right now because I don't have brain power or time, because that is not entirely simple. But of course, once we get there, now we can have. I think I may have gotten ahead of myself. No, I'm okay, actually. So we can have in the energy level number 3, we can have an L of 0, which is the 3s orbital. We can have an L equal to 1, which is a 3p orbitals, which again 3px, py, pz, or we can have L equals 2, which is the d orbitals, and those can have -2, -1, 0, +1, or +2. And then, because as you know, perhaps you may suspect, when we get to d orbitals, we have 5 different orientations for d orbitals. Again, I'm not going to go over d orbitals right now, but at some other point. Probably next time we'll go over d orbitals a little bit. But that is a lot of orientations. It surely is. And weirdly enough, all of those orientations are non-overlapping. And things get a little bit funky when we get to d orbitals. But it works. What can you say? It works. We can directly observe it. So. Okay. So the last thing here. Are they only 3-dimensional? So I mean, they still exist in 3-dimensional space. So you can depict them on like normal Cartesian coordinates. Oh, that's okay. No worries. So yeah, like the d orbitals, they just take on some slightly different shapes that are complementary to each other, but they remain non-overlapping. And again, I'll draw the orientations next time. But yeah, because there's definitely more discussion to have about that for sure. So the last number is ms, and that is spin up or spin down. And so this is just saying it's this or it's this, right? Just like in just like I've written in these electron configurations, one of them is always up and one of them is always down. And so that's the last part of what identifies each unique electron and yeah, like the rules for MS are really just that. And uh, the spin number of an electron is 1/2. Don't worry about what that means. Like, really, pretty much just ignore it completely for right now. But all this means is they're spin up or they're spin down. And again, just like with the other things that we were talking about with spin, I think last time, this does not refer to a physical spin. This is not a physical rotation or anything like that. It is a quantum physical property of these particles, because there's things with different spins. There's things with spins that are equal to 1 or 3 halves or 5 halves. All these different possible spins. Don't worry about what any of it means. Doesn't matter right now. Yeah, for our purposes, it just means that one of them points this way, one of them points that way, and that's all that we worry about. So using these 4 quantum numbers, these are just the address of each electron. So, like a 2px electron from fluorine would have n equals 2 because it's in the second energy level, an L equal to 1 because it's a p orbital, and ml of, it doesn't matter. This could be, let's just call it -1 for now, because the -1, 0, and +1 don't refer to any particular px, py, or pz. It's just one of them corresponds to each. I'm not sure if I'm explaining that super well. Do let me know if that's confusing, because I've nearly confused myself here. But it's just saying that these, one of these 3 is equal to one of these. Like, let's say px equals +1, pz equals 0, py equals -1. It could just as easily be interchanged any which way. All that this means is that there are these 3 orientations, x, y, and z, that these have to be in, and one of them is in each. Does not specify which one. So this could be -1 or 0 or +1, and I am writing that behind my head, so there we go. So yeah, the ML could be 0, like, it could be any of these, but it is one of these, if that makes sense. Right, because, okay, so, yeah, I know how I'll explain that. Very good. So, S equals +1/2. So remember that when we're talking about p orbitals, there's 6 of these. So there's 3 possibilities, like the energy level is 2, and the orbital type is p, but there's 6 electrons in there, and so there have to be 6 possible combinations of ml and s, and there's 3 for ml and there's 2 for s, which means you can have 6 different permutations of these, and so that's how we get there. So if we had n equals, let's say 1, L must equal 0 because it can be at most n-1. ML also must equal 0 because it is plus or minus any integer between plus or minus L, but that's 0 in this case. And MS equals -1/2. And this would be this could be the configuration for this guy. All right. So, I don't know about your brain. Mine is pretty well used up for today. I hope that made some sense. I threw a lot of numbers at you, and like like these quantum numbers. It's kind of a lot to take in, because it's just a lot of numbers and very abstract concepts here. But like the important takeaways is that the electron configurations follow a specific pattern that is described by these quantum numbers, and once you get used to what each of the numbers means, which is like these things, so it's like n is the 1 or the 2 or the 3 in front of the number, it's the energy level. L is just telling you what shape is the orbital. Is it spherical? Is it an s orbital? Is it a p orbital? Is it a d orbital? And then ML is saying within this orbital type, what is the orientation of the orbital this particular electron occupies? And then the MS is just referred to, is this electron pointing up or pointing down? So all of these are just a roadmap, an address for this electron in an electron configuration. All right. Okay. So I've been at this for 2 hours. I'm super done. Yeah, but I wanted to get at least through this part of orbitals. We haven't actually gotten into talking about how orbitals interact or anything. This is just the really like foundational stuff for what molecular orbital theory is. But like it's important things. It is this stuff, the mathematics behind this stuff tells us what the where electrons are in an atom. It tells us the shape of these orbitals. It tells us the orientation of all these electrons, and like this is the ground level of like where we start to learn about the actual chemistry. So it's heavy. It's very abstract because this is stuff that we have no intuition for. This is mathematical models that we have to assign meaning to. But this is what helps us rationalize what's happening in chemistry, and we can prove these models in experimental chemistry, and so like this is it's important stuff. So yeah, I hope that was not too brain breaking, and I will sign off here so that you can go and give your brain rest. I know I need to. But yeah, I really appreciate you coming by and asking so many good questions. I always really appreciate that. And yeah, I hope you have a lovely week as well. And I will see you on Friday. Okay, bye.